Even Jay Bradley Jr. sleeps sometime. Yeah, probably. Your coach is strange for his practice schedule. Okay, so chapter 14 is about solutions. And we've been using solutions in class, and this is going to go into some more detail on some aspects of it, and then a good chunk of it will actually end up being review of stuff that we've already done. And then tomorrow's lab, and what we'll pick up with when we come back from break, is also all about solutions. And so you'll be getting some things in the lab a little bit before we've talked about them. So realize that as you're going through it, make sure you just take good notes so that when you come back to answer the questions based on having maybe a little bit more information from lecture, it'll be good. But then the other thing is if you've done something in lab and then we go lecture on it, then you're like, oh yeah, we did that. That's the way it works. So what we want to do is talk about solutions. And the general idea is that, we skipped the chapter on gases, and then we have the chapter that's kind of on water, which is supposed to be a transition from gases to liquids, and now we're having a chapter on liquids is basically the idea. So we need to start by defining a few terms, and I think the first term we want to talk about is a solution. And a solution has two parts. It's one or more, and when we say one or more, we really are probably going to have just two for most of our solutions. So one or more substances homogeneously mixed or dissolved in another. And then what we're going to do is we're going to define some of the words in our definition, or at least make sure that we kind of understand it. So the first word we want to take a look at is homogeneous. Does anyone remember what that one means? That's actually review from chapter 1. Yeah, same throughout. Same composition, which also means the same chemical and physical properties throughout. So one of the things that we did very early in the beginning of the semester is we classified all mixtures, and we should point out that a solution really is a mixture from chapter 1. And it's a specific subset of mixtures. And so we're looking at just specifically things that are homogeneous, things that are very evenly mixed, that everything is distributed the same throughout, as opposed to solutions like, say, water and oil that separate. And then the other two parts we want to kind of look at is we said it's one or more substances, and then it's mixed or dissolved. We have a special name for that part of it, so I'm just going to put a 1 there so we have kind of a way to talk about it. That's what we call the solute. Solute. I hate these words because they all start with SOL. It's impossible to abbreviate any of these, so it's annoying. Although, actually, I technically have them. I just don't try to use them because it confuses everyone. So solute is the dissolved substance, and it's usually the least, or it has to be the least abundant component. So for example, if we said that we had a 1% milk, well, that milk is what we're going to term the solute because it's only 1% of the solution. And when we say we have 1% milk, we really mean we have 1% milk. That probably means we have 99% water. And we're going to learn that we're going to call that the solute, or solvent, I should say. So that's the second part of it. It's dissolved in another substance. And so the part that it's dissolved in is called the solvent. And one of the things you'll notice in this chapter is we have a lot of vocab in it. And it's important that we learn to use those words in the appropriate places and also not to mix them up. Like, I got to be honest, solution, solute, and solvent, since they all start with SOL, makes them kind of tough. So this is, yeah, I was going to say that, but it was too easy. Dissolving agent, and it's the most abundant component. And pictorially, I kind of like to think about it. This really isn't a Venn diagram. I don't know what the appropriate term is, but if this big circle represents my solution, then what's in the solution is a solvent, and dissolved in the solvent is my solute, meaning it's the smaller part. And so that kind of helps me keep track of which one. You've got solvent, or solution, solvent, solute. Or you can think about it as I've got what's dissolved in the solvent makes the solution. And when we talk about most abundant and least abundant component, that's because we can have things like, for instance, well, let's talk about vodka. Let's have some? No. Let's just talk about it. Maybe tonight. It is dollar drafts at, oh, I shouldn't announce things like that in class, probably, should I? You know, you can buy like 90 proof vodka, which is really just 45% vodka and, well, I guess it would be 55% water. Or you can buy the really good stuff, you know, that's, say, 180 proof, which is 90, I don't really know, I'm just making this stuff up. I don't drink that much. I don't know, can you get 180 proof vodka? Like Everclear, how about that? That's like, oh, well, then I'm just making this stuff up. 90% vodka and 10% water. And so notice that in one case, the vodka certainly is the solute because it's what's being dissolved in the water. But in the other case, we really have water being dissolved in the vodka. And of course, you can have a 50-50 mixture, in which case you really don't have a solute and solvent since they're both the same. But when in doubt, we usually just say water is the solvent, just because 99.9% of the time water is the solvent. Now, we can have different types of solutions. We're going to focus this chapter almost exclusively on solids dissolved in liquids, and liquids dissolved in liquids, and gases dissolved in liquids. But since there's 3 states of matter, that really implies that there's 9 types of solutions. And we're not going to talk about all types. We'll maybe mention a few of them here. But we can think of some of the ones. So for instance, if we say we have a solute and a solvent, actually, wait, 1, 2, 3. It doesn't make 9, it makes 6 technically, because we're making them pairwise. There's some math for you. So for instance, what if I have a gas dissolved in a gas? Can you guys come up with an example of that? How about air? Yeah. Air is a mixture of O2, CO2, etc. in nitrogen, because nitrogen is a major component of the atmosphere, right? So we are actually breathing constantly a solution of oxygen dissolved in nitrogen and a bunch of other stuff. What if I have a gas dissolved in a liquid? Can someone give me an example of that? I would say a fog is more like a liquid in a gas almost. What did you say, butane? Butane is kind of, it's something that's right at that gas-liquids interface. And so if it's compressed a little bit, it's a liquid. That's why they put it in butane lighters. But it has a very high vapor pressure, so it's very easy to get into the gas phase. So really, and also remember, a solution has to have 2 parts. So it's not just butane. It's got to be butane and something else. Let's see, who's drinking it this morning? No one. That's good. How about just pop? That's CO2 dissolved in mostly water and some carbon, or some sugar usually, or aspartame or something else equally nasty. How about a liquid in a liquid? That's pretty, well, actually maybe, well, see, like for instance, gas in a solid. I gotta be honest, that's pretty hard to come up with. But there are things called aerogels, where it really is like a gel-like substance that has lots and lots of little oxygen bubbles or gas bubbles trapped on the inside. It's how they make some types of foam. So we can have all sorts of these different types of solutions. How about a solid in a liquid? Just an example of this would be simply, yeah, you could just dissolve sugar in water. Or for instance, salt water. We have entire oceans where we just simply have solids dissolved in liquids. How about a solid? Now see, I can't think of a solid dissolved in a gas. I mean, arguably, you could say the process of, we learned about deposition last chapter, right? You can have, you know, like salt sea spray, for instance, like that, where it deposits the salt, right? Now, the question is it really dissolved in the gas or is it dissolved in the liquid? So a solid in a gas, yeah, I'm not so sure that's very easy to come up with. Let's see, what are we missing? Oh, we can have liquid in a liquid. That's pretty easy. That's alcohol. Booze. We already did a gas in a liquid, and we just did a solid in a liquid. And then we can try to dissolve things in solid, but it's pretty hard. I'm trying to think if I can think of a liquid in a solid. And then, of course, we did gas in a solid, and we'd have solid in a solid. Solid in a solid's easy. That's any alloys, like brass, which is a mixture, if I remember right, copper and steel. I don't really remember now off the top of my head. Something I probably need to make sure I have better in my notes. You can just see where my notes left off, where I got tired of coming up with examples and just said, you can do it off the top of your head. Not realizing that, you know, some days we have bad days where we can't do it off the top of our head. What? I would vote for going back to bed. So we've got all sorts of different solutions that we can talk about and do. So we can talk about properties of solutions then. And these are rules of thumb, meaning they're not 100%, which sometimes I wonder why we call them properties if they're not 100%. Generally, it's small molecules, meaning molecular or ionic sized, or about 10 to the minus 8, oops, that's an 8, not 18, to 10 to the minus 7 centimeters. The idea being that it's generally small. If we have larger particles dissolved in things, then we move into things that are called colloids, and if we go into even larger particles, we can talk about things that are suspensions. So really, we're going to think about mostly small molecules. They're homogeneous. We've kind of said that, but we'll kind of mention it. It means basically that they're uniform and they do not settle.
Isn't that word on the cartons?
That it's homogeneous? No, it's homogenized. Yeah. Homogenized means that it's been heat treated to kill any bacteria. Meaning, if you drink, I think you can drink straight out of the cow and it's pretty good. Pasteurization, oh wait, maybe homogenized is when they basically are saying that it's been thoroughly mixed so it doesn't settle out. Like if you let milk settle, doesn't the cream float to the top? I don't know, Jess, you're the expert on cows probably. I don't know, does anyone else have cows or goats?
Well, I don't know why they would put, why homogenized would make totally different meaning.
I think it's just that a lot of times you'll find they add fancy words to things that don't really mean anything or say exactly what was already true about it. The one I love now is no trans fats. Really, I'd never thought an apple had trans fats to start with. Or a lot of other products like that where it's like, no trans fats. Okay, wonderful. It never had any to begin with.
That is because consumers want to see those things.
Because consumers are idiots.
Exactly.
And that includes me, arguably, because I don't pay any attention to what I eat. Or, you know, low fat. Well, that's fine. They added an extra 500 calories of sugar in it, though, so it still has the same calorie part.
I know, like, no fat candy. I'm like, oh, good one.
Yeah.
Good one, gummy worms.
Good one. Exactly.
So it's the gummy worms, like 0 fat. I'm like,
They are physically separable. So we can remember that, for instance, if we heat a mixture of sodium chloride and H2O, we can boil off the water. And certainly there's other processes that we can use to separate those. They're generally transparent. But this is one of those that it's like, well, yeah, generally transparent, but can be colored. Needed the what? Okay, we can talk about, well, we can pause. Maybe I should bring those donuts over here. Yeah, we might not even cover all of this. Wow, that first homework has a lot of stuff. I doubt we'll even get through the first homework unless I start talking a lot faster. Which I'm not going to do. I'm just sort of nice and mellow, and I had weird dreams last night. I was building something and it was really strange. It exploded and then one of the parts went through the, it was in my grandma's basement apparently, and this is very strange since, yeah, and the part like exploded up through the floor and then left a huge hole in the carpet. I'm like, crap, can we just move the couch to cover it? None of you were in the dream, thankfully. Although one of the, I think, one of the aviation maintenance guys was. I think it was the crazy guy that wanted to build something. I was like, I don't think we can do that very easily. I'm not naming names.
The crazy one.
Okay, we have some qualitative terms. New page. I don't really know. I'm just telling you that because. So we have some qualitative descriptions that we can talk about. We can talk about things being soluble or insoluble. If you really want to make it nice, you got to take them the first time and then rewrite them. I've seen some people do that. They're so, and then if they're halfway through the sheet and they have to erase, they just crumple it up and throw it away. It's like, really?
That's my problem though. Like if I have to continue something on the next page, I'm really not happy about it.
So soluble simply means that a substance will dissolve. And insoluble simply means that the substance will not dissolve. And remember, we also have our solubility tables, where, remember we said if something is soluble, we wrote AQ next to it, and if something is insoluble, it had an I next to it. So that's kind of one set of terms that we've got. A second set of terms we can use are miscible versus immiscible. And miscible is generally confined to liquids that mix, meaning we don't talk about something being miscible if it's a solid in a liquid. So really the soluble insoluble part is generally a solid in a liquid. And this definition is really for liquids in liquids. So liquids that mix are miscible, liquids that are incapable of mixing are immiscible. That do not mix. And so for miscible, we can think of, for instance, ethanol and water. We know that they can mix in any ratio. Or something that's immiscible is like salad dressing. Basically, oil and water we know don't mix. And then the third set of terms, my God, all bullshit. You guys are just slow ass. Toss me the donuts, Jay Jr. Oh, you can just chuck them. And this is why he's not a starter. Did you see how far off that? No, just kidding. I have no idea if you're even a starter or not. Did you start? Yeah, it's kind of like every time I ask a kid on the baseball team to throw me something, it's like way over there, and you're just like, yeah.
And at like 80 miles an hour, really thanks.
No, that's the whole point. They can't throw hard either.
What's that?
What does it say number 2?
Above what?
The number 2.
The number 2? Oh, liquids and liquids.
Right,
You went to the game last night?
Yes, I did.
that's
It was disappointing and sad. Oops. I said that in tape. I'll go to the game tonight. Okay, so we've got one last set of terms. We can talk about unsaturated, saturated, and supersaturated. Which, if you ask me, supersaturated is one of those weird terms that really doesn't make any sense whatsoever, but certainly is a term we can talk about. So unsaturated means that there's less than the maximum amount dissolved. This is, again, solutions. We would probably talk about saturated, unsaturated, and supersaturated for solids and liquids, mostly. But we can also talk about it as gases, so basically anything in liquids. Saturated means that the maximum amount is dissolved. And this is why I think it's funny. So we have this word in the definition that is the maximum amount is dissolved in solution, but a supersaturated solution is more than the maximum amount is dissolved.
What is the maximum amount? How is it more than
And we're going to get there in a second, Jay. More than the maximum amount is dissolved in solution. The key here is that an unsaturated solution is stable, meaning if I stick it in a jar and put it on the shelf, it just stays there. A saturated solution is also stable, and a supersaturated solution is unstable, in that eventually the excess precipitates out. Meaning that we can have temporarily a supersaturated solution, but then as soon as that system is disturbed sufficiently, then it settles out. Some people may have seen this. It's kind of similar to, say, situations like where, have you ever taken a bottle of water or something out of the refrigerator? It usually happens to me with like a can of Coke or technically a beer. When you pull it out and you open it up and it freezes from the top down, like the second you disturb it, it actually freezes, but it's liquid before you pull it out.
That has never happened.
How did that happen with an otter pop?
Yeah, it also happens with outer pops.
Explain it to me again, maybe you have.
We're going to say it more than once because this is one of those things that's important moving forward. So another example of that would be, for instance, if you ever stuck something in the this is not the same example, but if you ever stick something in the microwave and the second you pull it out, it like boils over.
Yeah.
So that's basically where you heat it so high that it's actually above its boiling point, but until you disturb it, it doesn't actually start boiling. So the second you pull it out, it just goes, or, yeah, shake it or something. Or for something like this, what that would mean is I might have a perfectly clear solution, and it looks like I have everything dissolved in it, and I could put more substance in, but the second I drop, say, one little seed crystal in it, the whole thing crystallizes. And I can't remember, there's some children's thing that you can buy that makes little castles like that. Like you make a super...
Yeah, the sand.
Yeah.
That's neat. We should have that.
So something like that also works. So all of those are talking about sort of the same thing, but not the exact same phenomenon, which is essentially taking a system that appears stable, but is really unstable. And so Another example that's kind of like it for supersaturated but not as obvious, or not quite the exact same. For instance, if you make Jello, how many people have made Jello before? Or air. I should have imagined that. I didn't even think of that one. That shows you how slow I am this morning. So if you take, and you're making Jello, right, you heat the water up, you dump in all the Jello in it and whatever else you might want to put in it. And then when you cool it down, it solidifies, right? And that's because you've made a supersaturated solution at that temperature, and then as you're cooling it down, eventually you go from being supersaturated to the temperature at which you would be saturated, and then you go to the temperature at which you have more than the amount of dissolved in there that you should, and that's when it solidifies.
So these depend on temperature.
There is a temperature factor in there, and we're going to get to that next too. So a saturated solution is actually an equilibrium. And we've talked about, and I don't remember if it's this class how much we talk about it, but we've mentioned that term before, have we not? And we usually write equilibriums with these double arrows, right? Meaning something, a reaction or something goes both ways. Now we're going to have an entire chapter to finish up on equilibrium, and we'll also talk about equilibrium in chapter 15, so we're going to come back to it. But an equilibrium is basically a steady state between two states, and technically what it is that the rate of the forward reaction or process is equal to the rate of the reverse reaction. So if we kind of think about it, and I'll actually wait because I want to draw a good picture instead of cramming it into the margins. That would be a lot of work. Yeah, we won't get everything covered on 14A today. I have to go back and probably break this up at some point just because, boy, there's a lot of material in that first homework. And I haven't even looked at the second one. What is on the second one? Oh yeah, the second one's cake. Let's review. And then the third one, oh yeah, that's fun new stuff too. If you like math, there's a good chunk of math in this. You may have as many donuts as your mom allows you. I was going to say as many as he wants, but like I said, I'm afraid of Oksana, so. So, if I think about a big old beaker of water. I was going to have at least one more. Okay, so an unsaturated solution just has a few little pieces in it, right? Man, I drew that way too big. Here, we'll draw another one down here. A saturated solution is an equilibrium where we have some particles that are dissolved, but we also have a good chunk of the solid that is undissolved. This is, of course, water. Right. This would be what we consider a saturated solution. And what we mean by the rates being equal is that here, the rate at which particles dissolve, so the rate of dissolving, has got to be the same as the rate at which they precipitate. And so we can say that there is an equilibrium between the solid and the liquid in a saturated solution. And it's that equilibrium that, gets unbalanced when you have a supersaturated solution, but eventually the system has to return to it, in which case all of the excess solid that's dissolved in it will precipitate back out. Make sure we're checking everything else. So let's take a look at what effect. Bring me back my donuts. I want another one. Oh, they are back. This is the way to make lectures slow. Just have donuts and coffee and. I need to make it mandatory that you drink coffee in class. Then we could just fly through this stuff.
You need to make slides. What do you need to do?
No.
Yeah.
Exactly. I tried slides once. I really did. And all I did was read them faster.
You put a couple of fill in the blanks, following around, and then you can look at them later.
I don't know. To me, the art of writing is what solidifies and makes thoughts go in my head. And I know that that doesn't work for everyone, but it works for me and it works for most people, I think. So the precipitates. So the rate at which the solid dissolves is the same as the rate at which it precipitates back out. So every time a molecule or a particle dissolves, a particle precipitates back out to the solid. That's what we mean by equilibrium. That's what we mean by a saturated solution. Okay, can we go on? So, what affects solubility? Is this an affect or effects? What is the A one? Because I just never use it.
Cause and effect. Affect me like it would be something like you calling me a name.
That affects you.
Yeah.
Yeah, I'm never going to keep it track.
Tangible and affect is intangible.
Maybe.
Just that.
So what affects solubility? The first thing we're going to talk about is the nature. And what we mean by nature is we really mean the intermolecular forces of the solute and solvent. So if we think about it, we want to really realize that, well, this is really is an example, that 99% of the time, H2O is the solvent. And what that means is we know that water looks like this. We know that water has that separation of charge, and so we know that this is a very dipolar molecule. And we also know that it's capable of forming dipole-dipole interactions. We know that it can also form hydrogen bonds. And the reason I kind of list those separately is, even though they're the same thing, they're the attractive force between between partial charges, the key here is that one of them's kind of weakish and one of them's very strong. But it's capable of doing both. And it can even form, well, I'll use that as our next example. So that's the nature of our solvent. For our solute, I'm going to go to a new slide. Not yet. Okay, so for the solute, we have then two types of compounds that we can talk about. We can talk about things that are nonpolar solutes and things that are polar. Or we can even go so far as to say ionic is probably the easiest to think about. So what are things that are nonpolar? And this is going back to that chapter 11, right? So for instance, this is an example of a molecule that's nonpolar. Or for instance, carbon dioxide is a molecule that's nonpolar. It means that there's no separation of charge. Therefore, they do not interact with water and do not dissolve. Now, you can obviously dissolve a little bit of something in something else almost always, meaning it is possible to stick CO2 in water. But it's a very small amount, and it's because technically the CO2 undergoes a chemical reaction and forms carbonic acid. And really, we know that the second you open a can of pop, all the CO2 just begins fizzing back out. And so things that are nonpolar tend to not dissolve in water. Things that are polar ionic tend to dissolve in water. So an example of something that's polar, for instance, would be ethanol. So this is my structure of ethanol. And note that it has an OH bond in it. So this is capable of forming hydrogen bonds, of dipole-dipole and forming hydrogen bonds. And so if I have a methanol molecule, that can be surrounded by water molecules because of that dipole interaction. And that might interact with the hydrogen on a water molecule. There's a good picture in your book, better than I can draw, I'm guessing. And it might even be ethanol, I don't remember though. See if I can find a good picture. Maybe it's in a different chapter. I know it's in there somewhere. Maybe it's chapter 13. I kind of mix up a little with chapter 13 and 14 things simply because it's not too bad. Yeah, maybe there's not a good picture. Maybe I've just drawn it so often in my notes I think it exists. It's quite probable and possible. I'm firmly convinced that if you say something enough times, you begin to believe it. So for ionic compounds, an example of that would be, say, sodium chloride, sodium plus, chlorine minus. So what happens there is we can form what's technically called a Ion-Dipole Interaction. Don't worry about that term, we won't worry about it too much. Where we have an Na plus, and it's surrounded by a bunch of water molecules that are oriented with their minus side towards it. And so things like sodium chloride we know dissolve very readily in water. And the reason for that is because water is a polar substance, and polar substances have partial positive and negative charges. Those partial positive and negative charges can react with the full positive charge on the sodium. And then the chlorine can also interact with the positive charges on the hydrogens. And what you get is a shell of water that's dissolved sort of around each of those ions. I'll wait a second. There's a lovely picture of this on page 320. A much better picture than Jay could ever draw. 320. Now, Jess, that's not going to be the same in your version of the book. Yep. It's essentially the same picture I drew. Arguably, their picture is prettier. They draw it in colors and things like that. Arguably, my picture is more accurate or more informative simply because you see the interaction between the dipoles much clearer. They don't show those with dotted lines or anything. So we can summarize this idea with the idea that it's like dissolves like. That's our general rule for things. So if something's alike, then they'll dissolve each other. And if something's not alike, they'll dissolve each other. And what we mean by like, of course, is we're talking about their intermolecular forces. Oh, make sure I didn't ask any more detailed questions. I kind of skimmed over some of that. Maybe we'll do one more little topic. This one's reasonably easy. So the second thing that affects solubility is temperature. In general, if I have a solid dissolved in a liquid, increasing the temperature increases the solubility. Now, please note, these are general rules, meaning there are some compounds where increasing the temperature actually will decrease the solubility. But if you had to guess, for any random solid dissolved in a liquid, guessing that it increases would be right probably like 95% of the time.
What does that T stand for?
Temperature. Temperature. T.
Yeah.
Are you focusing, Jess?
Got all that, you're not writing.
You're actually ahead? Wow. Now, the rate or the amount that dissolves the rate at which it dissolves vary a lot. So again, this is a general rule. Sometimes it varies very little, and sometimes it varies quite a lot, meaning just changing the temperature 10 degrees, you might be able to double the amount of something dissolved, whereas for another substance, if you double the temperature, you can only put in another gram out of 100 or something, so you might only increase it 1 or 2%. And then the other major one that we want to talk about is gases dissolved in liquids. And here it's the opposite trend. If I increase the temperature, I tend to decrease the solubility. And for gases and liquids, there's a pretty easy way to kind of think about it. We've been talking about vapor pressure and everything, and so we should already expect that the solubility is going to be inversely proportional to the temperature. Because remember, the solubility, or the ability for a particle to go into the gas phase, is dependent on the amount of energy available. And remember, when in chapter 13, what we said is that basically if we increase the temperature, we increase the vapor pressure. That means that more molecules evaporate. More molecules evaporate. Therefore, that means we're technically decreasing the solubility of it, meaning there's less particles dissolved in there. So the idea is that if you give a liquid more energy, then a liquid goes into a gas, right?
Yeah.
And so less and less of it is dissolved. That makes sense. I mean, we know that solid to liquid to gas, it's all about adding energy, right? If you increase the temperature of any object, show me an object where you increase the temperature and it doesn't go from a solid liquid to a gas, and I'll give you a Nobel Prize. Well, maybe not a Nobel Prize. There might be like, someone can probably find one substance that does that, but I'm not sure I could name one off the top of my head. Don't think so. Not at all. So let's take a look at a graph. So in your book, this is really figure 14.4, and in the 10th edition, it's on page 321. I have no idea what page it's on in your current editions. And on this axis, we write grams of solute per 100 grams of H2O. And on this axis, we're simply going to plot temperature in degrees Celsius. So what I've been saying basically is that if it's a solid, and here I'll put some numbers on here. Here's 100, here's like 50, here's, well, 0, I guess. Not to scale. It's like some substances increase quite rapid. Temperatures will put 0 degrees Celsius, like say 20, 40, 60, 80, 100. So some substances, like I said, they start off with a very high solubility and they increase very rapidly. So this would be, for example, say NaNO3. Whereas some substances start off with very low solubility and it takes them a long time to kind of build up to something big. So this, for example, would be NaCl. And we have the rare exception to the rule. We've got some substances that will actually decrease in solubility. An example of that is Li2SO4, But remember, that's generally the exception. And so we can have a whole variety of these curves. Some of them will go up really fast, some of them will go up slow, some of them will start off higher on the graph, some of them will start off lower. And so there's all sorts of options. And then, of course, if we take a look at gases, it's pretty universal. If we have gases, they always decrease. So HCl gas or SO2 gas tend to always decrease with temperature. And we'll end with one last little fact. This will get you not all of the homework, but it'll get you the front page. And we'll talk about and start in on the back page. So it gets you something to get started on chapter 14. So if I take a look at one of these lines, if I have a point, for example, here I'll draw another line in another color, so we for sure are talking green here. So we'll call that line, I don't know what it looks like, che103 just for fun. If at any given temperature I'm above the line, this represents the unsaturated state, or supersaturated state, sorry. Supersaturated above the line. The line itself represents a saturated solution. And if you have, or are under the line, then that's an unsaturated solution. So for example, if you have, say, 50 grams of che103 dissolved in 100 grams of H2O at 20 degrees Celsius, is it unsaturated, saturated, or supersaturated? So what you do is you just plot that point. You say 50 grams of NO3 at 20 degrees Celsius is right here. So that's this. That is above the line.
But which line?
The che103 line, since we're talking about che103. So the green line. And so if it's above the line, it is supersaturated.
What's that thing in front of 20 degrees Celsius?
At. That's the at symbol. We'll pick up with this graph basically starting on Monday, and I'll actually print it off so that everyone has a copy too. That'll probably make your lives a little easier.
The graphs just don't make ever make sense.
We will talk then extensively about graphs in lab, office hours, or at any other time.
Graph.
You already know what we'll talk about in office hours.
We talk about everything in office hours. Okay, that's it for me. I don't know if there's a pre-lab for the lab or not on Thursday, so make sure you check